Okay, without further ado, let me start in on schedule and ground rules and so forth. Before I do though, thank you all so much for being here on Friday, the last day of a long week, a lot of information and a lot of talk that you've heard, but also a lot of great feedback from so many of you. Thank you for your participation, for your engagement. And with that, let's take a look at schedule, ground rules, and assumptions. And I'm actually going to go through these in a little bit of a reverse order. You've heard a little bit about Ralph's rules. You've heard about how we guided this program, this study, this idea, and James Mastandrea, whose newborn son came earlier this week, so he's been a big part of the program for the last couple of years. Very important influence on the project in terms of getting to where we are. Congratulations to him and his wife, but he's not joining us today on a regular basis because he's off doing more important things this week. So congratulations to James. But also he came up with this phrase, Ralph's rules. And as you heard about earlier in the week, we started with this idea of any technology included in this study has got to be ready for launch by 2030. That doesn't mean the launch date's in 2030, but we've got to make sure that we're not banking on miracles, on technological developments, or massive technology development investment, which comes with risk in order to make the meeting a reality. We wanted to make sure that we have a plan that can be executed. This word actionable has been thrown around in terms of what types of missions need to be considered for the decadal surveys this year, next year, and so forth. They want actionable ideas. They want things that they can look at and reasonably consider in the budgets that they have, that NASA has in the different mission areas within the Science Mission Directorate. That means that downlink has got to be achievable with the systems that we know are available. There are benefits and challenges to technologies like optical communication or X-ray communication, but the reality is that on the ground side, we need an infrastructure to depend upon. And so we are working in RF wavelengths that we know that the Deep Space Network is supporting now and expects to support over the decades to come. There isn't an optical ground network support system and architecture there that we can say, yes, we can definitely count on that. That's going to take some investment. That's one of the reasons why optical was taken off the table, for example. The power idea, 300 watts at 50 years, talked about this before. We know that the system can, the systems that are available, the RPS systems that would be available can accomplish this, but there is that longevity question. And as I said earlier, Clay Smith will dive into that a bit, and as well as the overall question of 50 years. But beyond Ralph's rules, there were other things. There were some other things that we had to consider. And we talked, you heard from Andy Dreisman yesterday about Parker Solar Probe and how that program went. This is modeled after Parker Solar Probe in a lot of ways. We consider this a large strategic mission for heliophysics. We consider the instruments, though we have put examples in there in order to show what kind of science could come back and what the budgets for mass and data and power and so forth have to be. But we expect that should this mission go forward, that the mission instruments would be competed, just as they were with Parker Solar Probe. Really open the aperture to allow people to propose the things that they believe would fit the bill, given whatever the actual mission requirements are down the road. But we also assumed and inserted, if you will, this idea of a disciplined mass budget management process. Ralph alluded to this earlier. Andy Dreisman hinted at it yesterday. On Parker Solar Probe, there was a very careful mass management program, if you will, where the instruments were not allowed to grow or out of hand and just keep adding mass and therefore cost and perhaps schedule and reduce overall mission resources. We have to make sure that we trust and rely upon the giant piles of data we have showing the relationship between complexity and mass and cost. And so we want to make this a mission that is actionable, that NASA could trust as something they could commit to. We want to make sure that that is high up in the ranking of what's important to this program. And then finally, there's some other necessary rules and assumptions that we applied as we went through this. We assumed that RPS would be available, that the plutonium and the system to provide the power would be available to this mission. And We heard from June yesterday that this type of system certainly could be available. Her priorities and their commitments come from NASA itself and not from a study like this. But we made sure that we weren't assuming something that they didn't even have to offer. And so we're trying to make sure that we kept everything within the right sort of constraints. We assumed in all of this that the cost for launch would be carried separately. Science missions typically do not include the cost of the launch vehicle in the budget that they say this is the mission budget. And we know that SLS has got its own budget questions and its own challenges, but we're not ignoring the fact that SLS would be an expensive launch vehicle, but we're not carrying that as a cost lien against this program. Just as with other science missions, we're assuming that that would be carried separately. Another thing that we took from the very beginning, and this came from the earliest discussions about this study and about what the mission architecture, structure, and timeline would look like, as we said, there's got to be milestones throughout Phase E. We can't launch and then have to wait 10 years for an exciting science reveal. We can't launch and say, in decades in the future, we'll get to the interstellar medium and then just sit and wait quietly until that happens. And so we made sure that as we explored the science options here, we went through, what is it that the instruments could be, should be, would be doing in the year after launch, in the 10 years that it's within the heliosphere itself. And the augmented mission is an expression of a larger set of things that would happen in that first decade, that first 15 years. But even without that, there are some very important science achievements that will happen immediately after the instruments start bringing back data, collecting data, and then results can be shared. We made sure that this mission would have, to be very clear, very good public outreach, engagement, and science results early on and throughout the mission, and not simply be looking towards that 50-year mark and saying that's where the value is. The value is right away. So together, these rules and these assumptions acted as guidelines to craft across the whole program. I'm going to take a little bit of a closer look at this milestones throughout Phase E for a second, because this is really important to us. We want NASA to know, we want the community to know that this mission, though we keep bringing in this phrase 50 years, this mission is about what happens right away and continually throughout the program. Pontus shared this on Wednesday. This is from his presentation on the science, operations. And you see here that in the inner heliosphere phase, there is line after line after line of science investigations, measurements, and results that come during that first decade of flight. And then once we get to the heliosheath, which will be a very exciting time for heliophysics because of the instruments that we'll be sending into this region. And as we talked about earlier in the week, Voyager's got instruments that have measured in this region, but they're not the ones that you would have sent if you said this is going to be part of our primary science. And so after that 12-year mark or 10-year mark, when we reach the heliosheath phase, we will see science that Voyager is unable to achieve. And then after that, as we get further and further away, you see that there are, again, line after line of measurements and results and return from this mission that continue. And we don't have individual milestones marked out on these, but I want you to understand that there are milestones built into this. There are ideas about what types of returns come back over and over again. And it's really this journey that the mission is on. And this is a phrase that we took from our sponsor's mouth herself. It's really, this is the mission where truly it's the journey that is the mission, and it's not the destination. And so keep that in mind as you consider all of what you've heard this week, that it's really the journey, and that this mission, day one after launch, we are underway. As soon as those instruments are deployed, we are returning science continuously for the next 50 years. Another way to look at this is we launch sometime in the 2030s. We get to Jupiter in less than a year, the fastest ever flyby of Jupiter between launch date and planetary flyby like that. And then not too far into the mission, once we get to the heliosheath, will be 2046 or so, 100 years since the first image of Earth was returned from space. 100 years shortly into this mission. And then in 2058, 100 years after NASA's birthday, we'll still be in the heliosheath doing primary mission science. 2076, America's 300th birthday, this mission will still be going strong. 2080s is the nominal end of mission, and onward. The spacecraft has the power, the communication system to continue into an extended mission phase should things be going well at that point in time. And so this is a different look at milestones. This is a different look at what that journey looks like. But we want over and over again to bring home that this mission, though it's about the science, and that's what's driving it, and that's what's crafting it, that has to be able to reach back to the people who are watching it, and the people who live around the people that are watching it, and be exciting to them from beginning to end. And so I'm going to talk a little bit about the schedule, what drives the program schedule. And it's really the planets aligning with the budget cycle. So 2023, 2022, 2023, 2024 will be 2024 at this point is likely to be the delivery date of the Solar and Space Physics Decadal Survey. So how many years after 2024 could a phase A begin? How many years after that is it going to take to get to a launch pad? And that's how we got to this notional launch date of 2036 and this notional launch direction here at the 180 degrees, 185 degrees, 85 degrees off of the nose of the heliosphere. And you see that it's this intersection of a high speed zone, a Jupiter flyby, excuse me, intersection with the ibex ribbon as it's been observed, and you heard a lot about the puts and takes on such a direction. But if 2036 turns out to not be the right year for it programmatically, we have exactly the same viability and science story, science power of a 2037 launch, of a 2038 launch, of a 2039 launch. And we know that the decadal surveys are being directed, and this new sense of the mission set is the 2023 to 33 decade, but that doesn't mean everything that is funded under those priorities has to launch in that decade. They have to launch having been started in that decade. And so we've talked to NASA to understand what this means. And so 2036 launch is very viable in terms of the direction for the Solar and Space Physics Decadal Survey, and these launch opportunities in the years that follow that very much give the sort of flexibility and strength of planning that NASA needs when considering a large strategic mission. And so we have this notional timeline for our basis of estimate on the cost. And you see here 12 months for conceptual phase A, 24 months for phase B, 600 months for phase E is a little bit unusual. But those first 4 lines there, phases A through D, are based very, very strongly on our experience on Parker Solar Probe. And so the instrument set, the mass of these instruments, the complexity of these instruments is on par with Parker. Integration and test is again on par with our experience with Parker, which launched in 2018. So this is not like a technology set or a skill set that is, not something that we're familiar with. We know what this takes, and these dates are based upon that. And you see draft plastered on the background of this. This is straight out of the mission concept report, which is still under draft. But we feel pretty confident that these dates make sense from a planning perspective and an estimate perspective for the cost. And so what does that look like in terms of a notional schedule? So the first one was a timeline. This is a schedule, given that Solar and Space Physics Decadal Survey, a science definition team that does the work that it needs to do, rolling into pre-phase A and a phase A. This could mean a phase A start in 2028, a phase B start in 2029, get to phase D in 2033 with a launch readiness of 2036, which corresponds to the trajectory heat map that we looked at just a couple minutes ago. And phase F ending in 2086, 2087. It's interesting to think about how much the world has changed in the last 50 years. The last 2 years has been quite a change for all of us, but we don't know what the world's going to look like in 2087. And so rolled into all of these costs, both in the A through D portion and then in the phase E portion are the tools and the activities necessary to prepare for a long multi-generational effort like this, and then to pay for that long multi-generational effort through phase E. And we've realized, and this was again some great feedback from the folks at NASA, that what we've crafted here, phase E could be looked at as 600 months and all of the cost of that, but it also could be looked at as essentially about the cost of a SMEX mission each of those decades. And that cost of that SMEX mission for operations would be not the entirety of a SMEX mission. It wouldn't be development and phases A through D, it would be phase E, but all of that cost applied to science, decade after decade. And so we look at the long-term large cost of phase E and we say, yes, it's of course big, but that's a function of time. And if instead we look at it across those planning cycles, the decades, each of the decades that follow could look at this and say, for the cost of a SMEX mission, we will be able to keep running this Vanguard mission, this flagship, best-in-class, global best-in-class mission to the outer solar system and beyond. Okay, with that, I have a few minutes for questions. If anybody has questions for me, I haven't checked in on the Q&A yet, but if not, we can take a quick breather and we can switch over to the cost discussion in a few minutes.